Record. All right. So last time we talked about PID control, bank control, and we touched on pure pursuit. I realized when I was prepping for this lecture that I made a small error in the derivation, so we'll just go through it again slowly to make sure that it's correct. So if you're going to do the homework, refer to these notes and these slides rather than the last lecture. I deleted them anyway, so you can't refer to the previous stuff. But yeah, just update your derivation to the one we're going to do today. But to kind of recap what we talked about filtering, then we started talking about control, and we discussed the idea of feedback control. You want to operate in closed loop where you're taking feedback and correcting for errors that you accumulate. Right? And so we started talking about feedback control. We described bang control, which is the stupidest method. Then we said, okay, we can do better than bang control, so we can do PID control, which is proportional, integral, and derivative control. Right? And we talked about some techniques to do that. Any questions, concerns about PID, or do we feel pretty comfortable? Good. Yes. Okay. So then we talked about PID control, but the issue with PID control is that it didn't use the model of the world. And so today what we're going to talk about is trying to recover pure pursuit and then cover an idea called LQR, and then try to work through LQR. LQR is a little bit like annoyingly complicated at the start, so you just go slowly and take as much time. Some logistics. Homework 2 is due this Friday. If for whatever reason you're not able to get it done by this Friday, it's okay. Let us know though. And we'll accommodate. We'll try to put our homework 3 on Saturday. Homework 3 covers PID control and pure pursuit. And we have extra credit, which covers like a fancier method called MPCI, which we'll cover next class. But we're still testing some things to make sure that it works. So it might be plus minus 1 or 2. And then we'll do reading, paper responses for control, not next Monday, but next Wednesday. And I'll send out the group assignments. Yeah. Okay. So that's logistics. Any other questions, concerns? Okay. Great. So the structure of our lecture today is we're going to recap your pursuit, rederive it a little bit. Then we're going to figure out how to go from tracking to optimal control. And then we're going to describe this idea called LQR or linear quadratic recursion. Great. So to recap pure pursuit, the idea of pure pursuit is kind of like chasing a carrot and stick. You want to set a look ahead goal some percentage ahead or some distance ahead, and then try to like change the steering angle of your car so that it is following some point that is ahead of your reference. So always setting a goal further ahead and then trying to follow it. And so the reason we want to do this as opposed to PID is that PID doesn't make use of the model of the world, a model of the car, and pure pursuit is making use of the model for this very particular class of vehicles, right? The class of vehicles where you can change the steering angle, like pure pursuit is specifically for that. It doesn't work for every system. And then we'll talk about LQR, which works for much broader classes, right? Okay, so what we want to do is try to incorporate this knowledge of physics. We work this out in our motion models, like we want to work it into our like controller, rather than just being reactive to errors. Okay, so that's the basic intuition behind pure pursuit. And the key trick we're going to use is the car is always moving in a circular arc. That's just always moving in a circular arc because we're going to say we're not going to change the velocity, just the steering angle. And in that case, if the car is always moving in a circular arc, you can just do a little bit of geometry to figure out what steering angle will get your circular arc to go to the point you want to go. So intuitively, you can think of like changing the steering angle changes the arc. You just want to figure out the steering angle that gets your arc to intersect with the point you're trying to get to. And so the pure pursuit controller is going to kind of build on the same car model, but it's going to assume that the car is moving with a fixed steering angle for some amount of time. And when a car is moving with a fixed steering angle with wheels rotated, right, it tends to move in a circle. Right, so we're gonna have basically a circular arc, which the car is going to move along. And what we want to do is figure out the steering angle, which gets the circular arc to go through the points that we want it to go. Yes. Okay. And the idea is that basically your choice of steering angle determines the radius of this circle, right? And so your choice of steering angle will change where the circle is going, and so this like steering angle will get the circle to intersect with the point that you care. So that's the intuition. Any questions? Okay. So, as we described earlier, we're going to have this car. We're going to choose some look-ahead point, right? You're going to choose a look-ahead point in the future, such that the distance between your current position x1 and your reference position is some value, which is your look-ahead distance. And we'll discuss briefly like what the look-ahead distance, what the choice of look-ahead distance does. But for now, let's just say we've picked a point, x ref, y ref, and that point is L ahead. Then we solve for a steering angle that takes us from our current position orientation to intersect with that point. So all that pure pursuit is doing is the circle. We just want to do geometry to get us to intersect with that point. That's okay. So we're going to do pure pursuit in closed loop. So we're going to, at any point in time, you're going to compute what angle is going to get you to your look ahead point. You're going to execute one step along that path. You're going to choose another look ahead point, which is further in the future. Repeat, 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 right? And so the point is that you like are chasing a carrot on a stick, so you're always putting your look ahead point ahead. Right? And the reason to do that is so that you don't just like go really windy to your target goal. Right? So you want a smooth path that follows your. Okay. So that's the intuition behind pure pursuit. Let's do a little bit of recap here, right? So if you remember our motion and tensor model lecture, right, we had these equations of motion. So we basically had our velocity, and our velocity is going to be our angle theta. So the portion along the x-axis is going to be x cosine theta. The portion along your y-axis is, or sorry, v cosine theta. Y-axis is going to be v sine theta, right? So it's just saying take your velocity and break it up into the components along each direction, right? And then we like introduced this idea of this instantaneous center of rotation. And so we said that the instantaneous center of rotation is the point which remains stationary when your car is rotating, right? And so this angle is going to be 90 degrees. This angle is going to be 90 degrees, right? And let's say if your steering angle is delta, this angle here is delta, right? Which means that tangent delta is going to be equal to this distance, L, which is the body length of the car, right? Divided by the radius of the instantaneous center of rotation. How far the instantaneous center of rotation is from the European. Because basically think about the car moving in a circle, right? And you can say that R is the radius of that circle, right? And so we're going to say tangent delta is equal to L over R. Right? That's the first thing that you have. And then we want to figure out like, okay, so we talked about how the X is changing. We've talked about how the Y is changing. And for the theta change, it's just the angular velocity, right? Which is equal to the velocity divided by the radius, right? And here the radius is equal to L over tan delta, right? So we have that the angular velocity is V tan delta over L, right? Just recapping geometry. So just think of this as like a circle. This is 90 degrees. That is delta. This is the definition of tangent delta. And this is just coming from the fact that angular velocity is V over R. And so you're just working out what x dot, y dot, and theta dot, right? Just to recap. Okay, do you feel good about this? If you don't, let's ask some questions. Okay. So I guess what we've done here is we've tried to re-express. We've tried to, this was what we did here was we found out what the change in x, y, and theta was, and so that was our motion model, right? In this particular case, you care less about your motion model. What you do is, what you want to figure out is this delta that gets you to a particular desired position, right? But let's just keep these equations in mind for a second, and we're going to figure out how they fit together, right? But essentially, whenever you choose a steering angle delta, this is how your x, y, and theta change. And your delta is always equal to L over R. Or tangent delta is equal to L over R. Yes? Okay. So those are the equations of motion that we had. And then if we go back to, our kinematic car model, we're going to choose a special case where we're not going to change the speed. Speed is fixed. We're just going to change the steering, right? And so our action in the system is just going to be the steering arm, not the speed. We're just going to try and follow the path. Okay, so that's just a little bit of a recap from last lecture, right? And so what we're going to do now is we're going to try and derive what steering angle gets me to a look ahead point, which is at a particular distance, right? And so we're going to try and do it on the whiteboard or my iPad. And so let's stop and ask me questions wherever this is. Makes sense, yeah. Okay, but basically you can think of, let's say your car here was at XY theta, okay? You can think of this being the instantaneous center of rotation. So this is your instantaneous center of rotation, right? And the radius of your instantaneous center of rotation, let's call it RPP, right? So now the RPP, so the way to think of the geometry here, this one is a little bit hard to see, so I'm gonna redraw the car here for a second. You can think of this is your target, this is your current position, right? So you have X, Y, theta, current position and orientation, right? You want to get to some point, which is X ref, Y ref, right? That's the point you want to get to. And what you want to do is you want to figure out the steering angle that gets you there. Now, to do that, you're going to have an instantaneous center of rotation, right? So let's pick the instantaneous center of rotation a little more pronounced than in this figure, right? So you can think of this as your instantaneous center of rotation. This is RPP. This is RPP, right? Just you can think of it like a circle, right? Okay. Now let's draw a right angle here, right? So this is going to be 90 degrees. You can almost think of it like draw a right angle from X ref, Y ref to the point from the car to the center of rotation, right? So we're just going to draw a right angle, and I'll explain why that matters in a second, right? And let's call this distance A, and let's call this distance B, right? Okay, so all we've done here is we've said car is going to move in an arc. RPP is the radius of the arc. We've drawn a right angle from X ref, Y ref to the line connecting the car to the center of rotation, right? And we've said the distance here is going to be A, the distance here is going to be B. Yes? Okay. Now, what we really want to do is find a way to we had this thing earlier where we had tangent delta is equal to L over R, right? When we had the car moving, we said the steering angle, tangent delta, is equal to L, which is the body length of the car, divided by R, which is the radius of the rotation, right? And so what we want to figure out is a way to express this R in terms of our desired position so that we can work out what the steering is going to be, right? So if we can express R as a function of X ref and Y ref, right? Then we can say that delta is equal to tangent inverse L by this R function, and then you know what your steering angle is going to be, right? So our strategy is going to be to try and express the radius in terms of quantities that we know. So we want to express in terms of X ref and Y ref and X and Y, right? And if we know how to do that, then you can work out what the steering angle is going to be. Okay, so let's go through this slowly, right? So we're gonna go in an arc from this point to this point. To go in this arc, we're gonna assume instantaneous center of rotation. And we know that with instantaneous center of rotation, a steering angle delta will have tangent delta as equal to L over R from our last, right? And now, so essentially what we want to do is if we know the center, if we know the radius that is desired, right, in terms of X ref and Y ref, then you can instantaneously get the steering angle delta by just doing tangent inverse, right? And so all we really need to do is work out what R is in terms of X ref and Y. Does that make sense? Ask me any questions here, otherwise I'm going to be talking to myself. Okay. So what we want to do here is we're going to try and let's see. So
So I have drawn this right angle triangle, right? And now I'm going to use some basic Pythagoras theorem, right? I'm going to say this distance here is going to be RPP minus B. Yes. And this is a right angle triangle. So A squared plus RPP minus B the whole square is equal to RPP squared. Right? Just basic Pythagoras theorem on this triangle right here. Okay, so let's try and expand this a little bit. You have A squared plus RPP plus B squared minus 2 RPPB, right? Just square expansion is equal to RPP squared. Yes. Pythagoras theorem plus expansion. You have a question? Missing a square and what? Correct. Yes. Thank you. Okay, so now you're just going to cancel these two out, right? And so you can have A squared plus B squared minus 2 RPP is equal to 0, which means that RPP is equal to A squared plus B squared divided by 2P. Right? Does that make sense? Okay, so now what we've done is we've expressed RPP. We've said, okay, we're going to get the steering angle by doing tangent inverse on L divided by R. And we're trying to express R in terms of these entities that we know, right? So we know X, Y, theta, we know where we want to go. And we're trying to get R in terms of things that we know. Yeah. So let's take stock of where we are. Okay, so just to consolidate, eraser is very slow, sorry. Okay, so what we know so far is that tangent delta is equal to L over R from our start slide, right? And we know that RPP is equal to A squared plus B squared by 2B. Yes? And now what we need, if we were able to figure out what A and B are, right? Then you can directly get delta is equal to tangent inverse of L divided by A squared plus B squared by 2. Okay? So where we are is we figured out tangent delta is equal to L over R from the motion model. We figured out that RPP is A squared plus B squared by 2B from trigonometry, right, or Pythagoras theorem. And we just use, put those two equations together. We have delta is equal to tangent inverse of L divided by A squared plus B squared by 2. Yes, or this 2B will go. And so essentially you will have delta is equal to tangent inverse of 2B times L divided by A squared plus B squared. Right? We still don't know A and B, but we're getting a little closer. Right? So what we've done is now we've taken our problem of figuring out what the steering angle is. We've written in terms of L, which we know, which is the length of the car, and these two things, A and B. And A and B are basically, if you draw like this right angle, like A is going to be the perpendicular distance, this B is going to be the pointer distance. Right? So we need to figure out what A and B are. But we've written out the steering angle in terms of L, A, and B. Yes? You're going to follow me so far? Now, the question of what A and B are is going to be easier understood if we just rotate the frame of reference a little bit. So I'm gonna, it's okay if I delete the stuff on this slide for a second. It's gonna be typeset on the next slide, but so if we, work out stuff here, we've said RPP is A squared plus B squared by 2B, and we know that tangent delta is equal to L over R. Those are things we know. And now what we want to do is express A and B in terms of quantities that we know. And so I think it's easiest understood actually by trying to imagine you take this whole frame of reference and rotate it. Okay. So we're just going to rotate the whole frame of reference and it's going to become easier to understand. So let me try and draw this. So imagine that you've rotated your frame of reference. And so now your arc was like that. Right. And your RPP was here, this was your arc. Now this was your A, this was your B, this is your instantaneous center of rotation, right? So it's like the same thing, just like rotate it. Yes. Let's take this picture and rotate it back. Okay. So then what you can see is that essentially in this is x ref and y ref, this is x and y, right? And so you can think of this as like in this rotated frame of reference, it's going to be B is going to be you know, the difference between x ref and x, and A is going to be the difference between y ref and y, right? So in this rotated frame of reference, this is if everything was in, you know, the origin frame, the distance like A would just be what is the difference in y's, right? And x would just B would just be what is the difference in x, right? Does that make sense? So like think of like this is xy, that's x ref y ref. The distance between these points you've drawn a perpendicular, just the difference between the x's, right? And the height is just the difference between the y's. And so if you had rotated the frame of reference, these would just be the differences. The problem is that you're not in a rotated frame of reference. And so this doesn't hold. So if you're in the zero frame of reference, this would hold. If you're not in it, this doesn't. Does it make sense? And what we're going to do is we're just going to try and convert it into a rotated frame. So, but you can think of like, what are A and B? A and B are just like the projections onto like the difference in x's and y's. So essentially, all we're going to do to work out what A and B are is we're going to notice that we introduced this idea of a rotation matrix, right? In our lecture, 2 lectures ago. And so all you're going to do is you're going to take the difference between x ref and y ref and x and y, right? So it's like take this vector, right, and rotate it so it's in a different frame of reference. And then that becomes A and B. Right? So you can almost think of like the rotation is saying that you know take x ref and x and project it and y ref and y, and that's going to give you what your A and B are. And if you remember what our rotation matrix was, our rotation matrix was just cosine theta. R for some theta is cosine theta minus sine theta, cosine theta, right? That is our rotation matrix, and we know what x ref, y ref are. So now what we've done is we've expressed A and B in terms of like all known quantities, right? And so let's like consolidate again, right? So we've said, hey, RPP is going to be A squared plus B squared by 2B. We've said A and B are going to be this thing, and this rotation matrix here is going to be cosine theta, sine theta, minus sine theta, cosine theta. Be a little careful with the signs here, right? Which is R minus theta, times x ref minus x, and y ref minus y. Right? This is going to be A and B. So we worked out what A is in terms of x, y, x ref, y ref, theta. We worked out what B is in terms of x, y, x ref, y ref, theta. Right? So now we have R as a function of all things that we know. Right? And so let's, if we put these pieces together, we have, you know, identity 1, which is saying this. You have identity 2, which is saying this. And then you have identity 3, which is saying tangent delta is equal to L over R, right? L over RPP. So if you have all of these pieces, right, then you can like plug them together to get your pure pursuit control. And so let's go away from my crappy handwriting to the whole controller, right? So we have tangent delta is equal to L over RPP. We have RPP is equal to A squared plus B squared divided by 2B. And we have A and B are equal to cosine theta, sine theta, minus sine theta, cosine theta, times x ref minus x, y ref minus y. Right? So this gives you the whole controller, right? Because now you can say delta is equal to tangent inverse L by R. R is given by this thing, and A and B are given by this thing, right? So if you had to write it in code, you start with x ref, y ref, x, y, theta. You compute A and B. Step one. Step two, you compute the radius, right? By a square plus b squared divided by 2b. In step three, you compute this J naught. Okay, I can see lots of you are lost. Ask me a question. I think the part of this, for me, that's the most confusing is the rotation.
Yeah, maybe, no, what about the rotation?
Yeah, so like let's try and go back. Let me see if I can destroy it. So think of like if you had the car at 0, 0, right? Like if the car was facing like the axes, right? If the car was facing the axes, right? Like if it is like perfectly axis aligned, right? In that case, what's going to happen is that if the car is perfectly axis aligned, this is x, y, right? And theta is equal to 0, 0. And then this is going to be x ref, y ref, right? And your radius is going to be some other point here. Okay? And so what we're saying is that the way we've defined A and B, we've said we're going to take x ref, y ref, and take the line connecting the instantaneous center of rotation and x and y. And then you're going to drop a perpendicular line to it, right? That's how we define A and B. Yes. So imagine that we're in a world where we're all axis aligned, right? Everything is aligned with the axes. In that case, what you've said is that this distance is A, this distance is B, correct? We believe that? Okay, now, if this is all axis aligned, this is X R, Y R, this is X and Y, like what is B gonna be? What is A gonna be and what is B gonna be, right? So this one is gonna be the difference between YR and Y, right? And this one is going to be the difference between XR and X, right? So if everything was perfectly axis aligned, then A and B would just be like the differences between the reference and the current position. Now, you're not axis aligned. So the problem is like the difference, like the problem is that the difference doesn't actually correspond to A and B because you're not axis aligned. So what you're going to do is going to take the vector, you're going to project it so that it is axis aligned. And then if it's axis aligned, if you're going to basically think of this rotation matrix, right, as changing the frame of reference. Rotation matrices change the frame of reference. Right? They're just saying you have something in one frame, you rotate it, so it's in another frame. Right? So I'm saying that if everything was in the unit frame of reference, then A and B are just the differences between X, Y, XR, Y. Now you're not in unit frame of reference, so your car is not 0, 0, right? So you're just going to rotate it by the angle of the car. That's it. Okay, so you're going to take the difference between XR X, YR Y, rotate it by the angle.
The axis aligned, usually it's like perpendicular.
Like, yeah, you can choose your frame of reference, right? But the point is that imagine that there was no rotation, right? If there was no rotation, in that case, basically, like XR minus X is directly equal to A, and YR minus Y is directly equal to B, right? So maybe it's easier if I like rotate it another way, right? So imagine the car was facing this way, right? And this was your X ref, Y ref, but there's no theta is equal to 0. Okay. So then what's going to happen is that, like, think of it this way. This is your R, this is your R, right? This is your R. This thing is A, this thing is B. Okay. So in this case, what is A going to be? Minus X. In this case, what is B going to be? Y ref minus Y. Right. So in the case where I think this angle may be easier to understand, but in this case, you can see A is directly equal to X ref minus X, and B is directly equal to Y ref minus Y, right? When theta is 0. When the rotation is 0, that the A and B are directly equal to X ref minus X and Y ref minus Y. But the car is rotated. And so you have to like rotate those things to get the A. So that's all right. So think of it as taking it at the 0 and then just rotating it back here. That's it. Does that make sense? Everyone with me? Okay, so it is important because otherwise your homework's not gonna. And then you'll be sad. I will be sad. So, 3 steps that you want to take, right? You're gonna have step 1 be computing A and B by the rotation matrix times XR minus X and YR minus Y. You're gonna take step 2, which is computing RPP is A squared plus B squared by 2B. And step 3 is you're going to compute delta is equal to tangent inverse of L by R. Yep. So those are your 3 steps for pure pursuit. Right? How do we feel about it? Good. Okay, great. So basically that's our pure pursuit algorithm. It's just like doing geometry to figure out what the steering angle is going to be so that the arc of rotation intersects where you want it to intersect. And try to break it down into these 3 things. Now, one thing you'll probably study this empirically, but it's the question of how do you choose L so that it doesn't make holes, right? The way to choose L here is if your L is pretty far in the future, right? Let's say you were here and you chose an L all the way here. You're probably gonna like skip a bunch of stuff in here. You're gonna take a slow arc, which is gonna like not track things very exactly, but it's gonna be nice and smooth. Because it's like your sphere is gonna be really nice and round, right? Whereas if so your steering angle is gonna be small. But if you choose an L, which is pretty close by, then you're gonna swerve really hard. So a way to think about how to choose your L is, do you want to stay very tight, close to your designated trajectory? In which case you choose a small L, but you're going to have to deal with more, sharp turns. Or do you want your trajectory to be more smooth? So then you set L to be larger. And if L is larger, then you have a smoother trajectory, which follows less closely. Yes? Okay. How do we feel about pure pursuit? Do we feel like we have an understanding of it? Any questions? Okay. Great. So I think that's the easy part, and now we're but basically we've talked about these controller design decisions, right? And we talked about a few different controllers. We've talked about bang control, we talked about PID control, and pure pursuit. Right? And we've discussed some advantages of each of them. Pure pursuit is nice, but it's very, very specific to this system. And so if you want to like make a humanoid backflip, I don't want to use pure pursuit. Nothing moves in a circular arc in that system, right? And so are we done? Not really. Right? We've figured out how to do a very specific control scheme, but we want to control general systems in robotics, right? And so what we're going to try and do next is try to move from these control schemes like PID, which are reactive, and pure pursuit, which is looking ahead, but it's looking ahead with a very specific model to a more general class of systems, right? And that's the difference between tracking and optimal control. Is like in optimal control, we're going to consider a slightly more general problem, right? So to motivate what we're thinking about, let's look at what the issues are with our current 3 options, right? The first issue is that both bang control and PID control are like, they ignore the model. They don't use anything about the model of the world. They're purely reactive. So you can't really get them to do like very directed behavior. So they're not using the model of the world. And the problem with pure pursuit is that it's using this like car moves in circular arcs model of the world, which is obviously not going to work for all systems. And so these models are very simplistic. And then the other thing is that all of them have a very particular cost, right? They're all trying to drive your system to 0 or drive your error to 0. And so they're all trying to do tracking, but you may want to have a more general cost, right? You may want to have a cost which weights positional errors higher than rotational errors. You might want to have a cost which tries to, not apply lots of force. And so you might want to have a more general cost function. And so these frameworks that we discussed just do not cover general cost functions. Right? The problem is, they don't cover general models, they don't cover general cost functions. Are they useless? No, like, you want to use these models in situations where you don't need these things. And a lot of times in like machine learning applications, you'll have something like PID control sitting at the bottom of your system. So you like have a learning algorithm, for instance, output positions for a PID control. So they're still very useful, but you have to think beyond that if you want to do more complicated control. Okay. So what we're going to do is we're going to try and reformulate control as an optimization problem. So we're going to consider a finite horizon problem. So you're going to act for 8 steps in the world, right? Let's say your robot is here. You're going to act for 8 steps in the world, right? And you're going to like try and figure out what is the cost of the H actions that you took by using your model. So your model here is going to tell you where the world is going to transition, right? You're going to try and figure out, I started here, if I took these H actions, how would I do? Right? So let's say now you have a cost function, something that takes in a state of the world and evaluates its goodness in some measure, right? And what you're going to do is you're going to try and take H actions, try and figure out what the cost was from 1 to H, right? Where xt plus 1 is equal to some function xt and ut, where function here is your model, right? And then you're going to try and minimize it. They're going to say you have an 8-step control problem. You started here. You're going to try and take a bunch of steps, right? And what you want to do is you want to choose the actions which lead to the lowest cost, right? So you just want to, like, that's why it's called optimal control, because you're trying to optimize the actions that lead to the lowest cost. But the system transitions according to the model, right? So it's like, this is where I was, I took this action, the model tells me this is where I'm going to be. And I'm trying to pick the series of controls that takes my system to a set of states that minimizes cost. Right? So the optimal control problem is just saying you know a model of the world, and you're trying to choose a series of actions that minimizes the cost. Right? If you're familiar with reinforcement learning maximizes rewards is just the opposite, is minimizing the cost. Same problem. So let's try and write this out more formally. Right. So we're saying that you want to choose a series of actions from 1 to t, that your system is going to choose a series of actions from 1 to t, such that when your system transitions according to the dynamics, right? In this could be like, for instance, our car model that we worked out, or a helicopter model, or a simulator. All of these are your model. You want to choose a series of actions such that when your system transitions according to the model, the states and actions incur minimum cost. Minimum cumulative cost, right? Not at every time step, the cumulative cost. Right. So this can encompass like pretty much, not all problems, but most problems. Essentially, any problem where you have some desired objective, any goal, you can cast as an optimal control problem. So these can be things like, do I want my trajectories to be smooth? Which point do I want it to go to? Do I want it to go through a waypoint? Do I want it to be less jerky, right? Any preferences you have about your system can go into the cost. And then any constraints you have on your system can go into the model, right? So you can say the actions cannot go beyond some level, or your model, your car can only move in circular arcs, like all of that goes into your model, right? So the model tells you how the world works, and C tells you what you decide. Right? And you're trying to figure out what are the actions to take to achieve what you decide. Everyone with me? Okay, so that's optimal control. And we have to figure out how to solve optimal control problems, right? So the problem with optimal control problems, as stated here, is that they're too hard to solve because F can be arbitrary and C can be arbitrary, and this optimization is like a pain in the ass, right? Like there's no like global solution to these problems. If F is nonlinear and C is nonlinear, and just like it doesn't work. And so what we're going to do is we're going to try and study a more constrained class of problems, right? So we're going to try and consider the class of problems where f of xt ut, right? You have an xt plus 1 is going to be a linear system, right? So it's the same thing we did in Kalman filtering. We're going to say, hey, the dynamics are linear, right? So that's the first thing. So it's linear dynamics. And then the second thing we're going to say is that the cost of any x and u is going to be quadratic. Sorry. Okay, so let's unpack this. It's saying that the system is always going to transition according to a linear system, right? So it's almost like y is equal to ax plus b, like here's xt plus 1 is equal to ax plus b t. System is linear, and your cost is quadratic. And the cost is saying that it's like quadratic in x and quadratic in b. Right? And so the things that define your system here are a, which is the coefficient that hits the state, b, which is the coefficient that hits action, q, which is the coefficient of cost that hits the state, and r, which is the coefficient of action in the cost. So any LQR system, right, is pretty much determined by combination of A, B, Q, and R. Okay. And so we're going to consider first a restricted class of systems, which is linear cost, linear dynamics, quadratic cost. Okay. We're going to try and solve it, and then we'll try to generalize to something that's nonlinear. Problem setting makes sense? So same thing we did in Kalman filtering. We're gonna, it's almost like essentially the same recipe. We're gonna construct some like very complicated linear equation thingy with linear costs and quadratic, linear dynamics, quadratic costs. And then we're gonna throw it all away and we're gonna do some sampling and it's gonna be good. Right, so, but it's important to understand how the LQR works. Okay, so that's our system, right? Try to understand what this system means. Let's say your state was n-dimensional and your action was m-dimensional, right? So vector. Right? Your xt plus 1 is going to be an n-dimensional vector. Your xt is going to be an n-dimensional vector, and your ut is going to be an m-dimensional vector. Right? And so to make this thing work, your A is going to be an n by n matrix, so it maps from n to n. And your B is going to be an n by m matrix, so it maps from m to n. Right? And so, go ahead.
So, y for b is n not.
Oh, because your actions might be different dimensions than your states, right? Like imagine that you had an arm where you can only control 2 joints.
Oh,
So your actions and your states are not always the same. Okay, so n is for actions, n is for states, this is your linear system. Right? Okay, so let's try and instantiate this in like a system that's often used, which is this inverted pendulum system. Right? So the inverted pendulum is basically you have a pendulum on a rod. You have like a little mass on a rod. We're going to assume that the rod is massless, but there's just like mass at the end. Yeah. And you can apply torque to like, there's like a joint, a motor at the base, and you can apply torque to the base, and you're trying to like balance the pendulum. Right? That's the problem. You're trying to apply torque to balance the pendulum when there's mass acting from the like, ball at the end of the pendulum. Right? So you can think of it as like something that's trying to balance. Yes. And so what I'm going to try and do is like instantiate this pendulum system and instantiate in the context of LQR. And then we'll try to solve it after that. Okay, so the equations of motion here are going to look something like this, right? You can almost, this is essentially like an F is equal to, this is like an F is equal to MA type equation, right? But it's basically saying this is like your rotational inertia. This is like your torque or like your alpha, the rotational or second derivative. This is your force that is being applied here, right? And this is your torque that is being applied here. So you can say this is just like coming from physics. You don't have to worry about like the details of the pendulum are less important than trying to instantiate it as a linear system, right? But you can think of this like you have mg, L sine theta projects it into the right angle. And then this is just the rotational equivalent of F is equal to M. Okay. And when you rewrite this a little bit, you can see that theta double dot is equal to J by L sine theta plus tau over ml square, where tau is the torque that is being applied to the base. Let's do a little bit of an approximation. So when theta is small, sine theta is approximately equal to theta. And so your approximation here is that your theta double dot, so your acceleration, right, is equal to theta times g over L plus tau over ml squared, right? So this doesn't look like a linear system yet, but we're going to make it look like a linear system. So the way we're going to make it look like a linear system is that I'm going to set my state to theta and theta dot, right? And I'm going to set my action to tau over ml squared. So maybe this is clear if I typeset it. Essentially, your state is going to be theta dot, right? So theta is your angle, theta dot is your rotational velocity, right? And I'm gonna try and rewrite this system over here in terms of a linear system, right? And so let's try and work through this, right? So we've said that theta double dot is equal to g over L theta plus tau over ml squared. Yes. So let's try and what we want to do is like rewrite this as a linear equation to show that we can express it as an LQR system. Right. So the exercise we're trying to go through is we have this pendulum, we're trying to express it as LQR, and then we'll figure out how to solve LQR. Yeah. So if you have this system here, you can say that basically theta t plus 1 minus theta t divided by delta t. That's basically theta dot t plus 1 minus theta dot delta t. That's the same thing as theta double dot, right? That's the definition of the derivative. Yes. And so that is going to be equal to g over L theta plus tau over ml squared, right? And so essentially theta t plus 1 dot minus theta t dot divided by delta t is going to be equal to g over L theta plus tau over ml squared. Yes? Just by the definition of the derivative. With me? Ish? So this is just coming from physics, don't worry about it. We're just trying to make it a linear system. So we're saying, okay, this is the definition of the derivative, which means that theta t plus 1 dot is going to be equal to g over L theta times delta t plus theta t dot plus tau over ml squared delta t. Right? So I'm just gonna multiply this on this side, take this over. So theta t plus 1 dot is equal to g over L theta delta t plus theta t dot plus tau over ml squared delta t. Right? Just like multiply both sides by delta t, shift over the theta t dot to the other side. Okay. And now if you look at the bottom equation here, right? What is this bottom equation saying? It's basically saying theta t plus 1 dot is equal to g over L theta t dot delta t, or theta t delta t, sorry, plus theta t dot plus tau over ml squared times delta t. Right? That's just the matrix form of what I just wrote. So I won't work through the whole thing, but an exercise for y'all is to basically take this equation over here, right? And then try to write out how does theta and theta dot evolve. And you'll see that it comes out to this linear equation. And this linear equation is one where basically theta and theta dot are our state, tau over ml squares are action, and this matrix over here is B, this matrix over here is C. Okay. Does that, the pendulum is not the important thing. I think the important thing is trying to like take a physical system and show that you can approximate it as a linear system. Like, and when you have a linear system, then you can apply it. Does that premise make sense? Okay, so I think we're close to out of time, but maybe some takeaways here are, we've talked about pure pursuits, right? So we've talked about pure pursuit. The only thing to importantly remember in pure pursuit is you want your arc to intersect with your reference point. Everything else is geometry. Then we talked about LQR. LQR then solves this optimization problem. And the important thing in your optimization problem is that you want to find
The actions that minimize cumulative cost, and you want to do it for a system that is linear and is for that. Okay, cool, thank you.